then we have a tensor, and we could take a third vector, put it there too. Now we have 3 subscripts, and we can continue this procedure as long as we want. And so one can make tensors of higher rank in this way. We can also go the other way. We can think about numbers. Well, numbers are kind of like tensors of 0, and they have no subscript. One subscript vector, think of it as a first rank tensor, 2 subscript second rank tensor, so no subscript, 0 rank tensor. So the world is kind of divided into these things. We have scalars. So these are numbers like pi, 14, whatever. Then we have vectors. And these are things with a single subscript, transformed in a certain way. Then we have second rank tensors, third, and so on. So we can think then scalars with some examples here. Example. Scalars. And so scalars are the number 3, pi, e, and so on. So we think of these as tensors of rank 0. How do these transform? If I change my coordinate system, what happens?
Nothing.
Nothing happens. Good. Vectors. So think about vectors. The electric field is a good vector. Velocity is a vector. More vectors. Acceleration, yeah, g. Yeah. Lots of examples of vectors. So these are tensors of rank 1. Second rank tensor, so we already said dielectric tensor, polarizability tensor, and then the process can continue, and we'll talk about other examples here a little later. But in nonlinear optics, for example, you can imagine a situation where the dielectric constant of a material, the dielectric tensor, depends on the electric field. So, for example, if you have a liquid crystal and you shine light on it, the electric field of the light can reorient the liquid crystal. And this reorientation will change epsilon. So you will have a kind of an effective epsilon. So you will have something that will depend on the electric field, and what you end up with will be like the dielectric tensor, or the polarizability tensor. So there you need something with 3 subscripts, right? 1 to combine with the electric field, and 2 left over to describe the polarization. And then you have 4th rank tensors. In elasticity, you have 4th rank tensor. So, yeah, so in elastic materials, you have stress and strain. Those are both second rank tensors. And if you want some relation between stress and strain, you need a 4th rank tensor. Just like if you have a relation between 2 vectors, you need a 2nd rank tensor. When you have 2 second rank tensors, you need a 4th rank tensor. So there's lots of other things here. People who study gravitation and other things, they like to deal with tensors.
How can we write down a 3rd rank or higher rank tensor?
Just put 3 subscripts. Well, how can you write it down?
Write it down.
Well, it's hard. You need a cube, right?
Yeah.
So it's kind of like a matrix with 3 axes.
Of 4.
You can think of, 3 regular matrices, one in front of each other. 4th, we cannot visualize. But it's hard. Okay, it's hard to visualize, but it's still there.
But it's easy to write down. You just have to write down all the numbers. That's all.
Okay. All right. So there's this. Now there are some special things that are very useful for example, there's the matrix of 1, 0, 0, 0, 1, 0, 0, 0, 1. That's a nice matrix, and so this is called the identity, because any vector that you multiply with this gives you the same vector back. So it's just like 1 in the tensor world, right? You multiply anything by it, you get the same multiple. And if you want to use an index notation, a subscript notation for that, this is the so-called Kronecker delta, delta alpha beta. So this is a guy which is 0 everywhere unless alpha equals beta. Then it's 1. So this is equal to 1 if alpha equals beta, 0 otherwise. And it's nice to write dot products with this. I have two vectors, A alpha, and B beta. So right now I just have the two of them. This is a matrix. And if I want to take the dot product, then I just multiply this with delta alpha beta. So you can imagine now what happens. I start summing over the alpha, and I will get 0 unless alpha equals beta. So this is the same as A beta, B beta. So it's a kind of a convenient
Why is
thing for doing this.
question?
Yes?
Then why, to use the alpha, the A alpha, B alpha?
Absolutely. It makes no difference what I write, right? It's just something which repeats means I have to sum. Doesn't matter if I call it alpha, beta, gamma, the alpha.
The only condition is that the sizes of alpha and beta are the same.
The what?
Or that the length of A vector and B vector is the same.
The less.
The length, I mean,
The length?
yeah,
How many
for example, alpha should change from 1 to 3 and beta should change from 1 to 3 but not from 1 to 5.
Yeah, they should be in the same space. Right? This is true. Yeah. Usually, it's good to define the space you operate in, and then the index of everybody goes through all the possibilities in that space. Okay. All right. So, okay. So this is fine. So we can add here delta alpha beta because it's a second rank tensor. I can write it either as I or like this. It's fine. Okay. Now what about cross products? So we were talking about dot products. What about cross products? Suppose I have A cross B equals C. I would like to write this in this index notation somehow. It's a little different from a dot product because I end up now not with a scalar, but with a vector. So A dot B is also a scalar, just a number. If I change my coordinate system, does this change?
No.
No, it doesn't change. So the components of the vectors change, sure, but this quantity is a scalar. It doesn't change. That's a kind of an important thing. So there are physical things which are scalars, which don't care about coordinate system. Energy, free energy. You can change the coordinate system. All the vectors will change their components. All the tensors will change their components. But scalars, they stay put. So that's a good thing about scalars. Okay, cross product. Can I do this in index notation? Yes? Probably. And how do I do it?
Definitely. You say that C alpha is some matrix epsilon alpha beta gamma times A beta B gamma.
Right,
And
exactly. Exactly. So we say C alpha is equal to some matrix epsilon Okay, this epsilon has nothing to do with dielectric tensor. This is some new entity. And because I want to end up with a vector, and I have two other vectors over here, A and B, I have to have three indices on this guy. So this has to be alpha, beta, gamma, and then I have A, beta, B, gamma. So I sum over this, I sum over this, and I'm left with one index, which is a vector. And this guy here is called what? Yeah, this is the Levi-Civita antisymmetric symbol. And if you work out the cross product term by term and meditate on that, then you can convince yourself that this epsilon has the following property, that if the subscripts are, and instead of x, y, z, I'm going to use 1, 2, 3. If the subscripts are 1, 2, 3, or 3, 1, 2, or 2, 3, 1, then this is equal to 1. So I could have used x, y, z too, but I think it's easier to see with 1, 2, 3. And now note what I have done here. I wrote 1, 2, 3, and then I took the 3 and put it in the front, left the other two unchanged. And then I took the 2 and put it here. This is called cyclic permutation, just moving things around. And then if I flip two of these, any two of them, it changes the sign. So if I have 2, 1, 3, it's the same as epsilon 3, 2, 1, or epsilon 1, 3, 2, and that's equal to minus 1. And it's 0 otherwise. Note that these are all cases when all the three indices are different. If any two indices are the same, thing is 0. So a third rank tensor in free space would have 27 elements, right? Because I can do 3 things in here, 3 things in here, 3 things in here, 27 elements. But this thing, in fact, among the 20, it has 3 of those 27 are equal to 1, 3 are equal to minus 1, all the others are 0. So it's a pretty sparse matrix. So this is a useful quantity too, and it's a third rank tensor, and it's used to make cross products in this way. And again, the order in which you write it doesn't matter. I could take this epsilon and put it in between these two. It would mean exactly the same thing. It's a summation of the indices that it determines what's going on. Okay. Now, let's talk about what happens under inversion of a coordinate system. So suppose I have a coordinate system, an x, y, z coordinate system. Let me erase most of this. Suppose we take an x, y, z coordinate system, usual right-handed coordinate system. So x, y, z. So this is a usual coordinate system. And suppose I have some vector in here, A. And then I invert the coordinate system. And by inversion, I mean I take each axis and I reflect it through the origin. So I'm going at an axis here, and an axis here, and an axis here. Okay? So this is going to be y prime, and this is going to be z prime, and this will be x prime. Okay? So just a new coordinate system. It's the same vector. What will be the components of this vector in this coordinate system?
Of what?
Hmm?
What? Of A.
Wait.
I didn't notice. I thought it's
The vector is the same. I'm just looking at the components. What are the components of a vector? I just project them onto the axis, right?
For minus in front of each component.
That's right, exactly that. So whatever we had before, I just put minus sign in front of it. So if I have a vector and I have this inversion of the coordinate system, then the components will change sign. Right?
So it's minus identity.
Components all change sign. All right. So if I have inversion, the components change sign. Components of a vector change sign. What about the components of a second rank tensor? Well, a second rank tensor is just two vectors. And if each of those vectors change sign, then the second rank tensor will not change sign. So, okay, so a vector changes sign, a second rank tensor doesn't change sign. What about a scalar? Doesn't change sign. Okay. What about a third rank tensor? That's like phi vector that changes sign. Okay. So, tensors of odd rank change sign under inversion, right? That is the components change sign when you invert the coordinate system, and tensors of even rank do not change sign. But now what about a cross product?
It's a vector. So it makes no sense.
It's a vector, huh? Well, but if this guy changes sign and that guy changes sign, this does not change sign.
Why not?
Hmm? Because this changes sign and that changes sign and this one doesn't. So there are these peculiar vectors which don't behave like proper vectors. And it turns out that, in fact, the world has to be split into two kinds of things: proper things and improper things. So these are proper quantities that we've used as examples. And then we can put improper things, which I'm going to call pseudo. So this is improper. So it's very simple. You have two vectors, and the components of the two vectors change sign. You write down a cross product. The cross product is made up of the product of two components of the original guy. They both change sign, the new thing doesn't change sign. So there are these funny things.
I have a question. Did I achieve a symbol is not a tensor? It's a metric, but it's not.
It is a tensor.
But if it's a tensor, it should be transformed as a tensor. And
That's right.
it means that it
Very
should
good.
change its side
That's right.
when that reflection.
That's right. It should, but it doesn't.
So then it's,
So it's kind of like an improper guy, right?
but we still call it tensor.
That's right. And so it's a tensor because it behaves the right way, except as far as the changing sign is concerned. So there are pseudo everything, pseudo scalars, pseudo vectors, and a pseudo vector is A cross B. And this is a pseudo vector because it doesn't behave the right way when we invert the coordinate system. Now, are there physical quantities which are pseudo vectors? Well, anything that comes from a cross product of proper vectors should be a pseudo vector. A magnetic field is like that. A magnetic field has to do with a cross product of R and a current, right? So it turns out that an H field and a B field, okay, well, this B is not a B field, this is just a vector, right? But the H field is a pseudo vector, and the B field is a pseudo vector. So E is proper, but H, because it's a fundamental definition, is a cross product of two proper vectors is a pseudo vector.
But if A cross B and, for example, B is pseudo, is the product still pseudo?
Yeah, so that's good. Now, yeah, so you can see how this has to work. That
Like the
if you have
false.
one pseudo guy combining with a proper guy, then it's going to be pseudo, right? Because one guy behaves properly, this behaves badly, the product will behave badly, right? But two pseudos make a right, and two wrongs make a right, so to speak. So we'll come back to that in a minute. And now, can I make a second rank pseudo tensor?
No.
Why?
Because if
You
you
just
change,
brought up an example. You just brought up an example, kind
I don't think you can make a second
of.
or an even rank. So
I take a proper vector, say the electric field, and I take its outer product with a pseudo vector, say the magnetic field. But this thing is a second rank tensor, it's made up from two vectors. This is proper, this is pseudo. So, second rank tensor, I ask myself, does it behave properly? I invert the coordinate system, this thing changes sign, this one doesn't, so this guy will change sign. That means it's pseudo. So we can make pseudo, second rank pseudo tensors this way. And the Levi-Civita, as Mikhail said, is indeed pseudo because a proper third rank tensor should change sign when you invert the coordinate system. The Levi-Civita doesn't change sign. It's always this. So here's a proper second rank guy, and here's a pseudo third rank guy. Okay. And this is really important to be aware that the world is made up of these things, because, you know, somebody could come up to you, well, let me put it off for a minute. What about this? Pseudo-scalar. Can I make a pseudo-scalar? Can I make a number that changes sign when I invert my coordinate system? Can I do that? Why not?
Zero.
Zero is an interesting choice. It's hard to tell when it changes sign. But this is a scalar. The dot product of two proper vectors is a scalar, right? If I invert, this changes sign, this doesn't, everything is good. But if I take the dot product of a proper vector and a pseudo vector, I have a scalar, and that scalar will change sign, right? So if I take A cross B is a proper vector, is a pseudo vector, and I dot it with a proper vector, I now have something that changes sign. So you can have scalars, just pure numbers, that will change sign when you change the coordinate system. Okay? And another example here would be E, the electric field dot H. Okay? So here we have a proper vector and a pseudo vector making a scalar. And so a good candidacy exam question is to ask somebody, can I have a term like this in a free energy? And yeah, at first you think, why not? But then, yeah, this is a pseudo scalar. This changes sign. The energy is a proper scalar. It cannot change sign. So these kinds of arguments can be really, really useful because based on symmetry, you can see what kinds of things are possible and what kinds of things are not possible. So this is second, for example. Okay? So the world is then, you can think of it being made up of tensors of various ranks, 0, 1, 2, 3, 4, and so on. We can deal with them easily using the subscript notation. And then all of these are divided into these two classes, proper ones, most things are in here, and pseudo ones, which don't behave correctly when we invert the coordinate system. So proper tensors, they change sign when you invert if the rank is odd. Actually, the vector will remind you of that. But they will not change sign if the rank is even. And the pseudo quantities are just the opposite. The even ranks change sign, and the odd ones do not. Okay? Good. So, good place to quit. And so dealing with these tensors, you will see makes life a lot easier, even though it may look a little complicated because of all these subscripts, but in fact it makes life a lot simpler. And when we do by itself a theory and look at the interaction between particles, you will see how this works. So for now, just get familiar with these ideas and make sure you're comfortable, with the definitions and how they work, and then we'll put these guys to use on Friday. Okay.